Hi, I am Apur Bapat, working with Altair Engineering Private Limited. Today in this video, I am going to show a basic theory of 2D elements. In today's video, I am going to discuss when to use 2D elements, different types of 2D elements available in HyperWorks. Then we will see how not to mesh, what are the industrial standards on how not to mesh. Then the quality checks, different quality checks available in 2D elements that we have to perform before going for the analysis. So we will start this with when to use 2D elements. 2D elements are used when two of the dimensions are very large in comparison to third dimensions. So when if you are talking about a sheet metal components or a plastic components like something dashboard or instrumental panels or something like that, so we perform a 2D meshing. So the 2D elements are used when the thickness of the component is very small as compared to the other two dimensions of the particular component. So in that scenario we use 2D elements. The element shapes available in for 2D element are quad elements as well as tria elements. Quad elements, as the name suggests, is a square element, where a tria element is a triangular element. Also a chord element, uh, it can be defined, means it can be simulated as rectangular, and tria elements, there is some modification as R trias can also be simulated. Then additional data from the users required by the software for simulating 2D element is remaining third dimension, that is the thickness of the component. So to simulate 2D elements, we need to provide thickness to the software. Then element types available in HyperWorks for 2D elements are thin shell elements, plate elements, member, plane stress and plane strain elements, axisymmetrical, solids, etc. These are some elements available for 2D elements. Then the practical application of 2D elements, where the mostly 2D meshing is done and simulation is done with using 2D elements, is sheet metal components, plastic components like instrument panels, as dashboard as I told, etc. Then now we will see family of 2D element, that is what are the different types of 2D elements available in HyperWorks. So basically 2D elements are divided in two categories, that is first is tria, second is quad. In tria there are two types of 2D elements available, that is first is linear tria, that is a first order tria, and a parabolic, P stands for parabolic tria element, that is a second order tria element. The first order, that is a linear tria element, is also known as constant strain triangle elements, and parabolic element, that is a parabolic triangular element, second order triangular element, is also known as linear strain triangles. Then in quad also there are two types of quad elements available, that is first order quad element and a second order quad element. In first order quad elements, the number of nodes for the calculation points are 4, and for second order quad element the calculation point increases to 8, that is second order quad element is a 8 noded quad element. Then we will see how not to mesh, what are the industry standards available for in industries that the meshing should be proper. So we will discuss them one by one. So there are some rules in industries which they follow for the meshing purpose of 2D element. First one is back-to-back triangles should be avoided. Two tria elements should not be connected to each other directly. So if you are doing a quad meshing or a mixed meshing, then maybe if you are performing auto mesh, it may be possible that triangular elements may get created, or if you are doing a remeshing, then also it may be possible that a triangular element may get created. So back-to-back triads are not allowed. That means one node should not share two triads, so that should not happen, because triad elements are more stiffer as compared to chord elements. So that's why back-to-back triads are not allowed. As you can see in the circular region, that these types of back-to-back triads are not allowed, that a single node, this single node is sharing two tria elements, so this type of tria elements are not allowed. Similarly in this node is sharing by two tria elements, this node is also sharing two tria elements, so these things are not allowed. Then on plane surface, triangular elements should be avoided, because there is a industry standard that if you are having a sheet metal part and if you are doing a chord meshing, then only a 5% of meshing, 5% of tria elements are allowed. So if you are having a planar region for meshing, you can avoid tria element as possible. So in planar region, the tria element should be avoided. This is another rule. Then we will move to the next portion, that is the third rule, which is no mesh transition on constant radius fillet curvatures. The mesh transition should be carried out on plane surfaces. This is because most of the in most of the components, the failure location are fillets or curved locations or a circular zones, that is circles or holes are on the components. So the fillets or the curved region should be meshed properly. There should not be mesh transition on that region, because if there is a mesh transitions, then the area of the element will keep on changing, and if the area got changed, as you can see, the area of this and this element is different as compared to this one. So these three have a different areas. Similarly, this is having a different one area and this is having a different area. So if the area is changed drastically, then there is a change in stress values, so because stress is dependent on the area. So if there is a drastic change, so the result will be not be appropriate. So to get appropriate result, you should not use a mesh transition along the fillets or curved region. You can use mesh transition on the planar surface, because many a times it has seen that planar surface doesn't go for the failure location. So if your part is having a failure location somewhere, so you should mesh that location properly without any mesh transitions or sudden change in element size. Then the fourth rule is circular holes should be modeled carefully with a washer of 1.5 to 2.5 times of its diameter, and a minimum of 2 layers around the hole should be provided there on the fillet or on the washers. This is because if you are simulating any bolt simulation or the fitting simulation, then the top head of the screw or top head of the nut will be tightened on that sheet metal. So to find the stresses generated by the pressure or torque from the nut bolt or due to that fitting, we should have a proper mesh around the holes, so that the simulation will be performed smoothly or accuracy will be high. So the another rule followed is circular holes should be modeled carefully with washers, and there is a rule followed that washer should always be 1.5 to 2.5 times of the diameter. Then the next rule is instead of zigzag distribution, structured or smooth mesh is recommended, because and a node aligned in a straight line. This is because if I generate a mesh something like this zigzag portion, so the force distribution will be same as this, and where there is a sharp deviation from the straight edge, so the force may get distributed in these two locations. So practically the force should transfer in single location, but due to the zigzag motion of the meshing, the force will get distributed in these two locations. So there is a force distribution will happen. So to avoid these type of errors, you can generate a smooth mesh, that is a straight mesh, and the force transformation should all then the force transformation will also be smooth or in a straight line. Okay, then the next and the last rule followed in industry are follow the feature lines, that is node should lie exactly on the edge. We should always try to follow the geometrical feature lines, that is these feature lines, these are the feature lines we should follow, because if we don't follow the feature line and if we do something mesh something like this, so by this we are not capturing the geometry properly, and if the geometry is not capturing properly, that means you are changing the dimensions of the geometry. So if the dimensions of the geometry got changed even by zero point 0.1 mm, the results may vary by a drastic percentage difference. So to avoid such type of failures or such type of errors, uh, always try to follow the feature lines given from the geometry. So always try to follow that. So now we will move to the next topic, that is the quality checks for 2D element. We will discuss one by one. There are several checks for 2D element. We will discuss one by one. So first one is warpage. This is the amount by which an element, or in the case of solid element, an element phase deviates from being planar. Since 3 point define a plane, this check only applies to chord. The chord is divided into two trias along its diagonal, and the angle between the trias normal is measured. Warpage of up to 5 degree is generally acceptable in industries. Ideally, the warpage should be 0, but the accepted values in industry for warpage is less than 10 degree, or it in sometimes it should not go beyond 5 degrees. Then the next check which we have to follow is aspect ratio. This is the ratio of the longest edge of the element to either its shortest edge or the shortest distance from a corner node to the opposing edge. So aspect ratio is the ratio of longest edge of the element to either its shortest edge or the shortest distance from a corner node to the opposite edge. For 3D element, each face of the element is treated as 2D element, and its aspect ratio determine the largest aspect ratio among these faces is returned as 3D elements aspect ratio. So the aspect ratio should rarely exceed 5:1. Ideally, the value for aspect ratio is 1, but acceptable value is 5. So aspect ratio is in general terms is defined as ratio of longest edge to the shortest edge. Then we will move to the next uh, topic, that is, or a next check, that is a skew. Skew of a triangular element is calculated by finding the minimum angle between the vectors from each node to the opposing mid surface, and the vector between the two adjacent mid side at each node of the element. The minimum angle found is subtracted from 90 degrees and reported as element skew. So skew angle is defined as the angle between the vectors which has been formed by the mid-side points of the adjacent mid-sides, and then this angle has been subtracted from 90 degree, and the remaining is known as skew angle. Ideally, the value of skew should be 0, or acceptable value for the skew is less than 45 degree. Now we'll discuss another quality check available in 2D mesh, that is chordal deviation. Curved surfaces can be approximated by using many short lines instead of a true curve. So chordal deviation is a perpendicular distance between the actual curve and the approximating line segment. So the distance between actual curve and approximating line segment is known as chordal deviation. So if I join these points and generate a curve, so this is the actual curve and this is the region of deviation. So this is the deviation zonal. So the perpendicular distance from the actual curve to the deviation is known as chordal deviation. Now we will move to the next quality check, that is minimum length. The minimum length can be defined as minimum element length are calculated using one of the two methods. That is, first is the shortest edge of the element. This method is used for non-tetrahedral 3D elements. That is, either it is used for penta element or hexa elements. Then the second method is the shortest distance from the corner node to its opposing edge or face in the case of tetra elements, referred to as minimal normalized height. So these are the two ways in which minimum length has been calculated. Then the next and the most important quality check for 2D element is Jacobian. This measures the deviation of an element from its ideal or perfect shape, such as triangles deviation from equilateral. The Jacobian value ranges from 0 to 1, where 1 represents a perfectly shaped element. The determinant of the Jacobian relates the local stretching of the parametric space which is required to fit it onto the global coordinate space. Hypermesh evaluates the determinant of the Jacobian matrix at each of the elements integration point, also called as Gauss point, or at the element's corner node, and reports the ratio between the smallest and the largest. In the case of Jacobian evaluation of a Gauss point, value of 0.7 or above are generally acceptable. So in general, Jacobian can be defined as, if ideally the shape on the global coordinate system should be like that, and due to the surface deviation or restriction of your element size, the shape of your element comes something like this. So transformation from the global coordinate system to local coordinate system is known as Jacobian. Generally, or the ideal value of the Jacobian should be 1, that is a perfect shape as of from the global coordinate system. If there is a deviation is there, so the deviation of 0.7 up to the deviation of 0.7 is allowed. Below that, we should always go and try to convert or make sure that these elements should be improved. So to improve these elements, we have different panels available, so we can improve the quality of Jacobian elements failing in Jacobian. So we will now move to our next topic, that is quality checks for 2D element. Then there are few angular checks are also important for 2D elements. We will discuss them one by one. Now the first one is triangular element minimum angle check. The minimum allowable interior angle for tria element is any element for which any interior angle falls below the specified value is highlighted and remains highlighted until you exit the check element panel or you select another check. Similarly, maximum angle is also important. So the minimum angle of the tria element is reported as 20 degree, and the maximum angle for the tria element is should be below 120 degree. So these are also very important check. So it has been calculated for all the three angles of the triangular element, and if the minimum angle for the particular element is coming below 120 degree, then it has been marked for the failure of minimum angle tria. Or if some of the angle is going above 120 degree for tria element, then it has been marked as failed triangles for maximum angle trias. Then the next point is minimum angle quad and maximum angle quad. This is same as tria element, that actually the quad element should have all the angles as 90 degree, but due to the geometrical influence, it may deform a shape. So the maximum angle and a minimum angle criteria for the chord element is the minimum angle should not go below 45 degree and the maximum angle should not exceed 135 degree value. So in this way we have ended with the theory of 3D element. Thank you.